Greetings everyone, this is Mr. Mullen. In this podcast I'm going to talk about some energy transformations that occur during simple harmonic motion. So let's go ahead and get started. In this lesson we're going to talk about the energy and the min and max values that occur during SHM. And relevant reading includes 14.4 in the night textbook, and a relevant assignment would be questions 1 to 5 on worksheet 2. So the objectives of this video are to explain that energy is a conserved quantity for a mass spring system vibrating in simple harmonic motion. And the second objective is to help you solve problems involving energy calculations for a mass spring system in simple harmonic motion. So let's go ahead and first off kind of talk about what is simple harmonic motion, abbreviated SHM for short. And basically simple harmonic motion is when we have this oscillations or oscillatory motion occurring in which there's a restoring force, and that restoring force is going to be acting, and it's always going to be proportional to an object's displacement from some equilibrium. So as long as there's a force that's restoring an object's position to an equilibrium position, and the farther you have an object away from equilibrium, if the force increases in a directly proportional way, we have what's called simple harmonic motion. So some examples of simple harmonic motion include masses attached to springs, pendulums swinging back and forth, tuning forks. A tuning fork is being pulled towards the center and back and forth, back and forth, back and forth as it oscillates. So let's look at energy is conserved quantity for a mass spring system. Let's look at a system that we're going to assume is closed and isolated. So in other words, we're going to have no energy going in or going out of our system. We're just going to be looking at the spring and the mass as it's moving along. We're going to ignore any of those non-conservative forces like friction. Also, in real life, this object would probably have some internal friction in the spring, which might eat up some of the joules of energy that we have, or friction on the surface. But in most problems, we're going to be solving for a simpler situation where the mechanical energy of the system is going to stay the same. We're not going to be losing energy. So we've seen problems like this in the past, where we have a ball in a gravitational field accelerating toward the Earth, and we're ignoring the effects of air resistance. If we have a ball sliding up a ramp, we have energy conservation if we're ignoring friction. We have a pendulum swinging back and forth. We have kinetic to potential to kinetic. So we have these energy conservation ideas. So here we have a mass attached to a spring, and most of the time we're going to see horizontal springs. We could also talk about vertical springs where there would be some gravitational potential energy we'd have to worry about. But most of the problems we're going to deal with involving energy conservation will be for horizontal springs. So I want to talk a little bit about this diagram that you see and show you some special cases. So I'm going to give you some more definitions and things to write down in a second. But I want us to talk about for a second is that if the mechanical energy total in the system is constant, so there's no outside, there's no energy going in or out of my system, then we've really got kind of two types of energy going on here. You'll notice that when it's moving, we've got that kinetic energy, and we also notice that when it stops for a second, like right there and right here, that it no longer has kinetic energy at those moments, but that spring that it's attached to is compressed or stretched. So it's really fast in the center, and then as we stretch or compress that string, we are increasing that amount of elastic potential energy. So we're really just looking at kinetic and elastic potential. At any 2 points on there, I've got some combination of kinetic and potential. So we've got some special places on here, kind of draw on some diagrams here. So when it's all the way stretched out, draw a little dotted line here. We would say that this is when our stretch distance of our spring x would be at the maximum stretch. So we have our amplitude there. But we've also got another place where the maximum amplitude occurs, and that would be, let me redraw this because I want to draw from the center of that object for a second. So bear with me here. So I'm going to go ahead and draw this from the center of that object. So there we go. Close. Kind of hard to stop this midway. So let's pretend for a moment that I could draw and freeze. There we go. Okay, so here's the maximum amplitude there. And you'll also notice that when it gets compressed again, we actually have another moment where it's stretched or compressed as much as it will be. So we have these kind of 2 points where we have these maximum amplitude stretched or compressed. And you'll notice in the center is showing that equilibrium length when this spring would not be stretched at all. So a couple special things occur here. When I reach all the way to the right-hand side and I'm at that maximum amplitude, then that total right here, we've actually stopped moving a moment when we change direction. So there's no kinetic. That means that it's all, kinetic is actually 0 here at that maximum amplitude position. So that means that all of the energy that's stored has to be, the total energy has to all be in the spring. So elastic potential energy, 1/2 kx squared. But instead of x, we actually would have that amplitude, 1/2 k, the stretch distance would just be a, whatever the amplitude would be. So that's going to occur at those 2 points. And then in the center, when the spring isn't stretched at all, it's moving when the spring has 0 potential energy, there's no stretch or compression, then we see that the mechanical energy total would be all kinetic energy, 1/2 mv squared. And I'm going to put a little max there, Vmax, because that's the maximum speed it could have right there at the center. And you'll kind of notice as you watch the animation that it really is moving the fastest in the center and the slowest at the end. It's kind of speeding up towards the center, and then once it passes that equilibrium position, the restoring force starts to act in the opposite direction of its motion to bring it back to equilibrium. So we slow down. So that maximum speed actually occurs right there in the center. So I want to kind of formalize and write down some of the stuff we talked about in the last minute or so. So if we have a frictionless system, then we would say that mechanical energy is conserved at all points during the oscillation. We've got that closed, isolated system. And if my spring is horizontally, then I know that the mechanical energy initial at any point is going to equal the mechanical energy final at any 2 points in the motion, wherever I could be. Now we said a second ago that the 2 types of energy that are going to be present on this oscillating spring are going to be the elastic potential energy and the kinetic energy, depending upon where it's at. And so the mechanical energy initial would be the sum of my potential and kinetic, whatever I have at that position. And then at the final position, it's also going to be kinetic and or elastic potential. So if I add those together, we should have energy being conserved. We should have the same amount of energy on each side. So we talked a moment ago about some of the special places, is that when the mass that's attached to the spring is at that equilibrium position, in other words, x is equal to 0, then you'll notice that there was no elastic potential energy because the string wasn't even stretched at all. And then we also noted that at the amplitudes, those 2 positions where we had the maximum stretch, compression, or stretching or compression, that it wasn't moving, it was changing directions there, and it was, kinetic energy was 0. There was no kinetic energy at all. It was all stored in the elastic potential at that point. Okay, so let's do some problems. So we're going to do some example problems from our handout. The first example is number 3. So it says we have a 5 kilogram mass attached to a horizontally orientated spring, and it gives us the spring constant there, 1800 newtons per meter, and it's saying that it undergoes simple harmonic motion with an amplitude of 80 centimeters. Part A says, what is the total energy in the mass spring system? Okay, so I have a horizontally situated spring, and we're going to ignore friction unless the problem tells us that it's there. So that means anywhere on the spring that I have possible potential energy if it's stretched at all, and I also have possible kinetic energy if it happens to be moving at all. So when I add those two up together, we're looking at the total energy that's available. So if they give me the amplitude, I know that when it's out to the amplitude that all the energy is stored in the spring. And there's no kinetic. So I can look at the elastic potential and say, okay, at the amplitude, it's all elastic potential. And so if I know the amplitude, I can actually solve for the total amount of energy. I know the spring constant was 1800 newtons per meter. And I know the amplitude is 80 centimeters or 0.80 meters. We're going to square that. And we're going to get our total energy in our system. It's going to be 576 joules of energy. All right, the next question says, what is the speed of the mass when it passes through equilibrium? Okay, so we're going through equilibrium so that I know my x is equal to 0. So I'm going to use my mechanical energy initial is equal to mechanical energy final. And it says at equilibrium is going to be my final position. Then I know that that's when my displacement for my spring is 0. And initially, we're looking for, that's where we're going to be trying to find. And then initially, we're going to pull back our spring, and we're going to assume that it's going to start from that amplitude that we've already established. So we're going to pull it back to 80 centimeters. And what that's going to allow me to do is we've already calculated the amount of energy initially if I pull it back that far. And so I have a mechanical energy initial now, 576 joules. We calculated that in the last part. And so if I pull it back to that maximum amplitude, I want to find out how fast it's going to be going at the center. So I know it's going to be all kinetic at that point when it reaches the center. So we've got mv squared. And it's all kinetic, of course, because at that position where it's no longer stretched, is at the equilibrium length. Remember we said that the elastic potential energy was 0 at that point. So it's just all kinetic. So I can actually solve now for my speed, v. So 1/2, the mass was given in the problem as being 5. And then we have v squared. And we can solve for my velocity. And that's going to be, we're going to be moving 15.2 meters per second at that moment. All right, so now we have kind of these extremes. The next thing says, how fast is the mass moving when the spring is compressed 30 centimeters from equilibrium? So this is now at a new position where it's kind of like moving, but it also has some compression in the spring. So we're still going to use energy conservation ideas. And our final position is we're trying to talk about when the spring is compressed to 0.3 meters. When the spring is compressed that much, we're trying to figure out how fast it's moving. So I'm still dealing with the same amount of initial energy. I didn't really lose or gain any. But now we're looking at the fact that there's compression. So we have some energy stored in 1/2 kx squared. And remember, they give us that spring constant there, so we can plug that in a second. And the bigger the spring constant, the more energy it takes to store in there. So we have that information, and then we have 1/2, and then we have mv squared. So now we have enough information to solve for all the stuff. So we have 576 is equal to 1/2 times, we've got that 1800 newtons per meter, and it was stretched 0.3 meters. We're going to square it, plus 1/2. The mass was 5, and the final velocity squared we're trying to solve for. So we can find that our velocity at that moment is going to have to be 14.1 meters per second, which is a little bit slower than it was at its max speed, and that's okay. And I could even go back on that. That was our speed, and put the max speed on there. And so this is obviously slower because some of the energy is stored in the spring now because there was a little bit of compression. All right, let's keep going. The next thing I want to talk about is some minimum and maximum values for velocity, or excuse me, displacement, velocity, and acceleration during simple harmonic motion. So I'm going to sketch a little diagram here. And we have, here's our wall where we've attached a spring. And I'm going to go ahead and draw down here. We have an equilibrium position of x equals 0. And I've stretched this back. So I've kind of got these two amplitudes. So this is where we have that positive amplitude. And this is where we have that negative amplitude if I have my object here. So it's attached to my spring. Draw my little spring here attached to the wall, and let's say it's moving to the right. And in the center there we have our equilibrium position. So looking at this diagram, I want to talk about, let's assume this is a frictionless floor, including any friction that's coming from the spring as well. So we've got a frictionless system. All right, so let's talk about first let's talk about velocity. So as I'm looking through here, when would the object be moving the fastest, and when would it be moving the slowest? So take a moment to think about that. Okay, now we're going to look at, remember we said that when it's at the extremes, at the amplitudes, that's when we are stretched or compressed the most, and it stops moving at that point. So that means in the center, when that restoring force is acting full effect to get it back towards the equilibrium, we've got that max velocity there, right there in the center. So we've got the maximum. I'm going to use a green pen here just so I can kind of have some color coding going on here. So we've got the maximum velocity is going to occur right there at that moment. And as I get farther and farther from that equilibrium position, what happens is, because Hooke's law holds true, as the displacement increases, I get farther from there, the force increases. So my next question is, well, where is the maximum acceleration value? And the maximum acceleration is actually going to occur when there's the biggest net force. And because the displacement is directly proportional to that force of the spring, that maximum acceleration is going to occur when I have that maximum displacement. So I've got that net force is equal to m times a, and for this problem, that force was the force of the spring. And Hooke's law was telling us that the bigger the spring, the bigger the compression or the stretch distance, the more force. So if I have the biggest net force there, then those are our values for the maximum acceleration. So looking back, when the spring is actually at equilibrium, well, then there's no net force because there's no restoring force when I'm at equilibrium. And that would be when we have zero acceleration. So I'm going to use a red pen for all that because we're kind of talking about some negatives, zero and negative values here. So we've got zero acceleration here, and that's because there's no force from the spring at that point. So it's going to have the lowest acceleration. And the last thing I want to talk about, the minimum values for velocity. And we said that the minimum values for velocity are going to occur when we have the object changing direction. It has to come to a stop. and all that energy is going to be stretched out. So we've got our minimum velocities here, and the reason why that's the minimum velocity is because all that mechanical energy is in that elastic potential form. Minimum velocity. Okay, so these are some important places on a mass spring oscillator where you kind of need to be familiar with, where does it have the maximum and minimum values. To test your understanding, we're going to do example number 4. So we have a mass spring system constructed by connecting a 2 kilogram object to a horizontally oriented spring. They give us a spring constant of 42 newtons per meter, and we're going to displace that mass from equilibrium and release it to oscillate in simple harmonic motion. The diagram to the right is a graph of the position reached by the mass during its cyclic motion with equilibrium, and the 2 amplitudes have been marked. So just kind of take a moment, maybe pause the video, label the locations on the graph where the mass experiences its maximum position, speed, and acceleration, and then label the locations on the graph where the mass experiences 0 speed and 0 acceleration. So take a moment to check your understanding, pause the video, and here we go. We're going to go ahead and come back now. So we have the, let's start with the max values. So we have the maximum position is going to occur when we are the farthest away. When we've pulled back the spring to its amplitude, then the spring is at its current maximum position. It's not going to be any closer, not going to be any farther from 0. So we have the maximum displacement then would occur there, and then maximum displacement would occur over there as well for our maximum displacement or maximum position away from the reference point. Looking at the velocity values, we said that it was moving the fastest in the center. So we have our maximum velocity there. And then it had the maximum acceleration when the spring force was the greatest, and that occurred when it was stretched out the most. And those were at the two ends. And then for our zero quantities, it came to a stop before it turned around at the end. So we had 0 velocity at those 2 points. And then at the middle, when there was no spring force anymore, then there was 0 acceleration at that instant in time. All right, I'm going to just update this here, change in position, displacement. All right, so we have one more final example that we're going to do. All right, and for our last example, what we're going to do is we're going to look at the energy situation to find the maximum values for the position, the speed, and the acceleration experienced by the mass. So I'm going to start with the first thing I want to find is the maximum position. So this, of course, occurs when the mass is stretched as far as it can go. So I'm going to look at energy conservation to guide what we're doing here. And I'm looking at that position where we reach that maximum amplitude, because that is exactly where my kinetic energy is non-existent. We've stretched it out completely. So I'm going to go ahead and I want you to notice that I've rewritten the problem here. So if the mass is moving at 3.5 meters per second, that is going to occur at a location of 0.93 centimeters. So if you can just update the problem that you have in front of you to make that change. So we stretch it out, and as it's going back and forth, we take a snapshot when it's at 0.93 centimeters. So when our x is at 0.93 meters. Okay, so what we're going to do is we're going to use our conservation of energy ideas. Initially, it's both moving and the spring is not at its equilibrium position. It's 90 centimeters away. So I've got 1/2. I'm going to use the spring kx squared plus 1/2 mv squared. And at the end, all that energy is going to go into stretching out the spring at that maximum position. So I'm going to put A as my position, that amplitude, and it's going to be squared. So I have enough information given to me now in the problem. So I'm going to solve for, we know that the spring constant was 42, and the stretch distance was 0.93 meters, and we're going to square that, plus 1/2, the mass was 2 kilograms, and we were moving 3.5 meters per second. We're going to square that, so it'll equal to 1/2 times 42 times a squared. Alright, so when I simplify these numbers, I'm going to get 30.41 is equal to 1/2 times 42a squared. And when I solve for A, my amplitude, I'm going to get 1.2 meters. So that is the maximum position when it's completely stretched out. All that energy goes into stretching the spring. The second part of the problem says calculate the max speed. So we're looking for V max. So we have to remember when that occurs, and we want that to be at the equilibrium, when it was right in the center, and it was at where there was no elastic potential energy, right when the spring was not stretched at all. So I'm going to use mechanical energy conservation ideas again. And our final is we're going to be looking when it's at that equilibrium position where there's no spring stretching or compressing, and the elastic potential was 0. So we've already calculated how much energy is in our system, 30.41 joules. And so if there's no elastic potential, that means it's all kinetic. And so we're going to be looking for that maximum possible velocity value. And so when I solve for V max, I plug in my mass of 2 kilograms. We're going to get to that maximum velocity of this spring oscillator would be 5.51 meters per second. Alright, step 2 is done. The third part says calculate the maximum acceleration of the mass. And remember, this is going to occur when that force is the greatest. So when I look at Newton's second law, F equals ma, and that force, because of Hooke's law, is going to be equal to k times x. And so when I plug in my mass, which was 2 kilograms, times the maximum acceleration I'm looking for, I know that it's going to be equal to that spring constant, 42, times the amplitude. And the reason why I'm putting the amplitude on here is because that maximum acceleration happens at that maximum position. At that maximum position is when we're stretched the most, therefore the force is the most, therefore it must have the greatest acceleration. So when I solve for A max, we're going to get that the maximum acceleration is 25.2 meters per second squared. And there we go. All right, I hope that this podcast has been helpful, and enjoy the rest of your break.